But when you use colors to identify this speed limit, you find there is a break. So these are green, but there is a red link within it. And you can easily identify that this is incorrect. So use colors to help you. The next tip is to use 3D mode. If you simulator supports, use the 3D mode to check for superimposed nodes. What does this mean? Superimpose. Just overlay something put right above each other, right above the other. So in some network, there may be nodes overlapping at one location. And these can be checked using the 3D mode. For example, you have two links crossing each other, and if the elevation or the z value of each node is not correctly input, you can use the 3D mode to check it. The next tip is very recommended, which is to create a report summarizing the attributes so that their values can be easily reviewed. So prepare a report, not only view them on your computer, but create a paper report to summarize them. So in this way, everybody can review it and can help you find the problem. The last tip is to understand the warning messages. Warning message will not affect your result. At least they won't stop you. They won't stop you from running your model. But warning messages are always carrying very important information. So before you check your error, at the stage of error checking, try to understand all the warning messages. Now, the third stage of your error checking is to review animation. Now we start to review animation. Before this stage, we are all checking them in a static way. Now we want to review animation. To review animation, it's not very simple as just running it. First step is to run your model at an extremely low demand level. So for example, your demand level was 100%, then you run it at 1% or 10%, extremely low demand level. The reason of doing that is because when you run your demand at a low level, you save a lot of running time, right? You save a lot of simulation time. And your simulator doesn't have to do that much calculation. And another reason is when the demand level is very low, you don't expect any congestion. So theoretically speaking, all the vehicles should be able to run very smoothly, quickly, without any congestion. And in this way, the network is not so congested, so it will be easy to trace a single vehicle. And in this way, you can trace single vehicles through the network, and you can see where they are expected to slow down. So if they slow down, you will find the problem. And you can repeat this for several different OD pairs. For example, you check some vehicles from the south, the bottom of the network, to the top of the network, and from the west to east. Let them travel a long distance and see if they have problem. So the goal of this step is to trace single vehicles. And after that, you may want to change the demand level higher, but this time it's changed to 50%. And this 50% demand level is usually not high enough to cause congestion. So this time you check if the 50% demand level is going to cause any congestion. If yes, there must be some problem. Okay? So the review animation just consists of these two steps. It doesn't require you to use 100% demand level, because that will be the task of the next step, calibration. Okay? Okay, so by doing this, we have already validated our network. We probably have fixed some errors. Now we can proceed to the next step called calibration. First, let's talk about the definition of calibration. This is a formula, my formula for simulation. We have three inputs: network, demand, and parameters, simulation parameters. Then we put all of these things into our simulation model, and we get our output. Right? That's a simulation process. In calibration, we want to adjust this part, parameters. In the error checking, we want to check the network and demand. But in the calibration stage, we want to check the parameters. The reason for checking parameters is that the default parameters that are provided by the simulation model or software package will not be able to reproduce every local traffic condition. So there is no model, no set of parameters that can be used everywhere. So when you are modeling Buffalo, you have to change your parameters to Buffalo's network or Buffalo's traffic conditions. Here is the importance of calibration. In the literature, in 2003, I think 2003, they mentioned 13% difference in the predicted freeway speed for the existing condition will increase to 69% in forecasting scenario. So if you don't calibrate this 13% difference, in the future it will increase to 69%. And as I mentioned, no single model is equally accurate for all possible traffic conditions. And all the models are providing those default values, but they are not reliable. Now here is our calibration step strategy. You know what you want to do, but this is not an easy task. It's very difficult. And even after this lecture, you will still be uneasy. But I hope it will be a bit easier. The calibration can be divided into three stages. The first stage is called capacity calibration, which is to calibrate the capacity of the network. The second part is route choice calibration. The third part is the system performance calibration. So let me introduce them one by one. Before doing that, I want to emphasize some concepts in case you don't remember them. Flow rate. So we have volumes on each link that you already know the concept of volume. But flow rate is very similar to volume. That means how many vehicles are passing a point. But flow rate is different in that it has to convert all kinds of vehicle types into a standard vehicle type, standard passenger car. So trucks will be multiplied by a factor. And in this way, we can get flow rate. So the unit of flow rate is still vehicle per hour, but that's for a standard vehicle. Then capacity. Capacity indicates the maximum flow rate at a point. Then we have discharge headway. Discharge headway means when you have a queue. For example, there is a queue waiting at a stop line when there is the red signal. When the signal goes green, the vehicles start to discharge. The queue starts to discharge. And each vehicle is waiting for a discharge headway, which means you are not starting your vehicle until the vehicle ahead of you is already so far away from you. So that's the discharge headway of a queue. Discharge headway of a queue. The fourth concept is the acceptable gap. When you are crossing, when you are, for example, when you are making a left turn, you want to make sure the opposing through movement, the opposing traffic leaves you a certain gap. Otherwise, you won't be able to turn left. You can check these concepts in H-Highway Capacity Manual, the file I gave you. Now, let's go back to calibration of capacity. This stage has several substages. The first stage is called substage is called collect field measurements of capacity. This just means when you want to do calibration, you first have to get some data. So you want to calibrate your capacity, then you first have to know what the real capacity is. For non-signalized facilities like freeway or non-signalized intersections, we use this Q discharge rate to indicate the capacity. So let's say we have here's a place of congestion, and we have accumulated a Q here. For example, we have only one lane. Let's say we only have one lane. We have accumulated a Q. Then we start measuring here. So we can check how many vehicles can be discharged per any time interval, or per any per 15 minutes. So this is Q. This is Q. When we measure here, when here is a Q, let's measure how many vehicles can pass this point at the time unit. So this is for non-signalized facilities. And if we are going to measure the capacity of signalized intersections, we use saturation flow rate. Saturation flow rate, which also means when there's Q, multiplied by effective green time divided by cycle length. And in some cases, you are not allowed, or you are not unable to get all the data, to get the capacity data. So what can you do? There's an alternative, which is to use high capacity manual if your data is unavailable. So you can use the formulas to calculate those capacities when you cannot collect them in the field. After collecting the real capacities, you may want to obtain model estimation of the capacity. So that was the real capacity, and that's the simulated capacity. And how do you obtain these capacities? Similarly, the simulation models are not going to give you a variable or an output called capacity. They won't tell you how big the capacity is. You still have to measure it. To measure this capacity, you can temporarily increase the demand to cause congestion, and then use the saturation flow rate or Q discharge rate as we defined earlier. So in the simulation model, the advantage is that you can easily change the demand to cause congestion. And sometimes you will see force bottlenecks. The bottlenecks that exist in some places that shouldn't have bottleneck. And these force bottlenecks must be cleared. The way of doing this is to change some attributes of that bottleneck